Hi everyone, I'm Massimo Zambelli and I'll be talking about how we are dealing with the problem of handling a lot of data to empower research in our AI technology team. The work I'll be presenting was developed mainly by me and my colleague Alessandro Berlati. In academia, a lot of effort is made in advancing models, trying to beat the state of the art in terms of accuracy or speed. In industry though, the real focus is on data. With good data, in fact, on one end, we can gain a significant competitive advantage by training models which are well specialized on the tasks we want many spoons to excel at. On the other end, as you can see in the chart at the right, in a machine learning pipeline, dealing with data takes up the vast majority of the total time. Thus, it's really important to have an infrastructure that is able to effectively deal with data in the most automated way possible. Dealing with data to empower research in particular poses very peculiar challenges. For instance, we need to support multiple projects at the same time, which can be often very heterogeneous and span from classification, which is the case, for instance, with shortcut detection in videos, to state-of-the-art generative models for image enhancement, which is a core feature of Remini, one of our main apps. To feed our training pipelines with lots of diverse data, we also need to be able to gather samples from many different sources, which can be public datasets, private datasets that we acquire somehow, but also media that the users agreed on sharing with us. Crucially, in doing so, we must uniform the information to a standard, because think about creating a training dataset from multiple sources. We need at least the labels to match and have the same semantics. Additionally, since we need to process millions of images per day, we need a fast and reliable pipeline, which is also privacy compliant. Of course, tools exist, and just to mention a few, we tried V7 Darwin, Dataloop, SuperAnnotate, and 51, but we found out that the industry is still pretty unable to provide satisfactory flexibility and performance to satisfy our needs. So we decided to build a tool of our own, our dataset manager, which is composed of Metadata Extractor, cloud storage, and analysis and retrieval features. As you can see here, the architecture is quite simple, but yet very flexible and completely cloud-based. It's composed of three main components, the first of which is the Metadata Extractor, which is a set of machine learning models which aim at extracting high-level semantic features. For instance, they perform face and object detection, quality assessment, and scene recognition. The samples and the respective metadata are then fed into the data zoo, which is composed of cloud-stored buckets and databases. The dataset manager takes care of the entire flow, and it also provides a UI to gather data comprising visualization, analysis, and filtering of the samples. To better illustrate what the dataset manager is supposed to do, we can consider the case in which, for instance, our AI researcher needs to improve Remini's face and answer on people wearing glasses. That's a very likely scenario because it's often the case in industry that we want to improve the performance of a model in a very specific case. This is quite difficult in general, but with our tool we can combine multiple datasets that lie in the data zoo and filter them by the presence of glasses, which is a metadata that we extract as part of facial attributes. Thus, we get a new dataset composed of only faces from people wearing glasses, and we are straight away ready for training. Mind that additional, more subtle challenges may hide in the data, and that's often the case in a real production environment. For instance, we can have long-tail distributions where some characteristics happen to be much more likely than others. And this is the case with glasses, as you can see in the right chart. This is sometimes an issue which can be tackled, for example, through data augmentation or custom sampling. The good thing here is that by integrating our dataset manager with our training API, which we are developing in-house too, we can provide custom transformation and sampling algorithms based on the statistics of the gathered data automatically. Of course, the most AI-intensive module is the Metadata Extractor, and so it's worth explaining much more in detail. As anticipated, we do not only extract information about faces, but we can also precisely detect objects and recognizing entire scenes. So, for instance, the giraffes on the right are predicted to be in a field road or forest path, while the two supercars in the image in the middle are detected to be in a parking lot. Both of the things match very well with what we can see. Getting back to the previous running example, we may now want to improve the background enhancer on foliage, which is pretty tough to reconstruct precisely. Filters can be applied to create datasets based on scene labels and tags, and we can run the metadata extractor, for instance, on images coming directly from our customers. Here we can see samples that get correctly tagged with vegetation, foliage, or leaves, and also they are labeled as a finer variation of forest. Or perhaps we just want to take a look at pictures with cute pets, so we can filter on the presence of dogs or cats. At the core of our metadata extractor, we have different models, which of course are trained in very different ways and on various datasets. For face attributes extraction, image quality assessment, and scene recognition, we use a variation of the popular ResNet model. While for object detection, we use YOLO v5, and for face detection, Retina Face. As a significant example, and given how important faces are in our pipeline, I'm going to give a more detailed explanation of the latter. So just to give a bit of context, face detection is a special instance of object detection where we only have one class, the face. The model starts from a set of anchor boxes scattered all over the picture, which they are represented here in light blue. Then the model has to perform two tasks. For each of the anchor boxes, it has to it has to predict, let's say, the likelihood that a face is in that anchor box. And secondly, it has to perform a regression task where it has to refine itself to try to match the real bounding box of the face, which is the one we can see in the picture at the right. In the case of Retina Face, we also obtain 5 landmarks which can be useful for subsequent tasks. They are in particular the corner of the mouth, the tip of the nose, and the 2 eyes. Subsequent tasks can be very important in some contexts, and one of them, the most popular one, could be face alignment. Retina Face is based mainly on 2 big ideas. The first one is that learning different aspects of a face can enhance the knowledge gained by the model at training time, and thus the performance at inference. Besides the usual task of classification and regression, which I just mentioned, the authors of the paper, which present Retina Face, also use the regression task on the face landmarks, but also a self-supervised task which entails learning to re-render a face given a 3D mesh of it. Of course, this is a more advanced topic, and details can be found in the paper. I will limit myself to the second idea, which is that of using feature pyramid networks that help improving detection of small objects. In fact, in a convolutional neural network, which in this case is composed of convolutional layers and max pool layers, the more we go into it, the more the features will represent high-level semantics. And that's due to the fact that mainly we are enlarging the field of view. So basically the net is able to see much bigger portions of the initial image, but this means that details are lost. Feature pyramid networks are able to empower usual backbones, usual CNNs, with the ability of exploit earlier features, which thus contain information on smaller portion of the image, by incorporating also high-level context into them. As a result, we will have different levels of the pyramid that work well with different object scales. And this is very well exploited in Retina Face, where the features at each level are associated with different sets of anchor boxes with correspondingly different sizes. So high-level features are associated to bigger boxes and thus bigger objects, bigger faces, and low-level features to smaller ones. Here is the original paper which presents Retina Face. If you want more details, you can refer to this. But for now, I will go back to our dataset manager, saying that we plan for the future to empower research across all our products by means of it, supporting also our in-house training API. And additionally, we strive to implement powerful advanced features that no other tool provides yet, like support for continuous learning. That's everything, so thank you very much for your attention.